And you can go back and forth, but of course, division by 0 when you have coefficients here is something to think about. So I know this is a new idea, right? So how do we solve, what is an exact equation, right, is the question. Let me show you. So let's see here, if I come up with an example. What example are we on? 4, 5? I forget. Okay, so, I mean, I guess I could do the circle, but I think I won't. Suppose you have x squared dx minus y squared dy equal to 0. So I'm just starting us off in the Pfaffian form, right? Understand that this is in some sense just a shorthand for like solving for dy dx, right? But looking at it this way allows us to use total differentials to understand it, right? So this we can look at as what? This is really the total differential of what function? Let me try to guide you through the thought process. Some of you might guess if I give you a second. Let me try to head that off at the pass. Partial f, partial x, we want what? X squared. And we want partial f, partial y to be minus y squared. So what should I put here to make that happen? Can you see it?
Partial f, partial x. Minus partial f, partial y.
I need to, my question is what should I want this up here to actually be literally df. Okay, what f makes this into df? What's that? The gradient. Well, but the thing is I don't know what f is. What is f? No, oh, all right, well. So if I have partial f, partial x, fine, I'll no guessing, all right, well. Integrate this with respect to x, right? Well, fine. I mean, I feel like we should use partial x there because it's a partial integration, right? We're integrating with respect to x, holding y fixed. This says what? This says that f is equal to 1/3 x cubed plus a constant, but the constant is actually a function of y, because we're integrating holding y fixed, right? And then I also need that partial f, partial y equals to minus y squared, right? But if I differentiate this animal right here with respect to y, what do I get? I get partial c1 partial y equals to minus y squared, right? But of course that partial derivative can be written as a total derivative because c1 is just a function of y. You can do this integral, right? What's c1 equal to then? Right, c1 is minus 1/3 y cubed plus c2, where c2 is an honest to goodness constant. Can't be a function of x because c1 is just a function of y. Put it all together, what we have? F of x comma y is equal to 1/3 x cubed minus 1/3 y cubed plus c2. Now I don't really care about the c2 there, right? Any function that has the total differential of x squared dx minus y squared dy will do. So just forget about the c2 and you can put a 1/3 x cubed right here, right? Minus 1/3 y cubed. This is a way, I'm just rewriting the differential equation as a total differential, right? And then, well, this discussion over here shows you that, you know, if you look at the level curve, right? F equal to a constant, that makes what? That makes the total differential be 0. So once I can recast the differential equation as a total differential equal to 0, the solution follows immediately as what? So there you go. That's the solution to the differential equation. I don't require you to derive the level function. Like usually one of you guys will step in and guess it for me. But I guess you're just still kind of first day of class kind of stuff, whatever. Like this right here, I don't require you guys to do. I think it's totally reasonable to guess that from this. Let's try another one. Maybe you can guess the next one. Let's try again. Let's try again. I'm sorry, have you been so browbeaten that you have to derive it, that you feel like you have to derive it, even though you know in your heart you can guess it? What's the deal? I don't know. How about xy plus e to the x dx plus xy. I'm not sure this works. Just a second here. Uno momento. I was thinking. Well, maybe you guys figure this one out. By now you guys are like wise to my trap. Let's see here. Yeah? Oh. You're going to guess it for me? So what's the guess? Now let's see here. If we take the differential of this, right? What we're going to get is 2xy squared plus e to the x dx plus 2x squared y plus secant squared y dy.
Get rid of the extra x squared y squared.
See, so what Travis did, which is, Travis? Yeah. It's totally reasonable, is he integrated the x piece with respect to x, he integrated the y piece with respect to y, and he just added them, right? That's what he did. But you have to be a little bit more careful than that. You have to look for pieces which come from both integrations in common. See, this x squared y and xy squared and x squared y term both come from the differential of 1/2 x squared y squared. So I only need one of those. That one term automatically generates both this and that is the thing. So just get rid of the 2 and we're good to go. Okay, so thank you for your guess. Now the solution, 1/2 x squared y squared plus e to the x plus tangent y equal to a constant. That is the implicit general solution to this differential equation. These are not hard, right? I mean, but then the question is, so can we always do this, right? Can you always do this? Well, no, can't always do this. There are some differential equations which are exact. There are some which are not. All right? We'll talk more about that next time. But in the remaining time, I want to show you how we can derive the integrating factor method from exact equations. So what is the integrating factor method problem? Remember it? What was our problem? We had dy dx, right? Plus py equals to q. What's that? Oh, I still have it over there? Oh, good, good. I'll leave that there. So if I rewrite this in Pfaffian form, what's it look like? dy equals to q minus py dx, right? And just to make the, complete this, so I get py minus q dx plus dy equals to 0. Now here, p is just a function of x and q is just a function of x, right? And if I tried to do the exact method here, it wouldn't work. I guess I need to tell you why. I'm sorry. So if f is exact, right? If m dx plus n dy, this is like the typical notation for this Pfaffian form. We use m and n like this. If it's exact, that means that this is actually equal to the total differential. I'll try to unpack this more slowly next lecture, but we just need it for a second here. If this df is equal to that, that means what? That means that m is partial f partial x, right? And n is partial f partial y, right? But how are partial derivatives connected? Oh well. So if we calculate partial m, partial y, that's partial squared f, partial y, partial x, right? Which is partial squared f, partial x, partial y, which is partial n, partial x. So if a differential equation is exact, there has to be this intertwining condition between the coefficient of the dx and the coefficient of the dy. If it's not the case, it's not exact, which means we can't obtain it as the differential of a level function. But the cool thing is, Pfaff's theorem states that you can take any differential equation relative to some conditions I forget, multiply it by that integrating factor and make it exact. So Pfaff gives us the inspiration to try I times py minus q dx plus I dy equals to 0 for, and since we're lazy, we'll say I equals to I of x, all right? So Pfaff's theorem gives us the courage to try this. And then if I want this to be exact, what condition do I need in I? This is my m. This is my n. I need partial m, partial y equals to partial n, partial x, right? So can you take the derivative of this with respect to y? I is a function of x, p is a function of x, q is a function of x. When you partial differentiate this with respect to y, the only thing that's got a y in it is y. So the partial derivative of this with respect to y is just ip. And ip is equal to what? So it's supposed to equal to be partial n partial x, right? So that is partial I, partial x, but that's dy dx because I is just a function of x, we're assuming it. We'll talk more about making these kinds of assumptions as we go on in the course. Oftentimes we make assumptions. You might ask why we make those assumptions. The answer is because we can. I mean, you can make up any number of assumptions you want, The question is, do you make so many assumptions that you can't? You know, for example, you could want a mate that was both attractive and smart, and you know that might be too much. I don't know. Let's see here. Oops. No laughing. Oh no. Have I offended you? Let's see here. So I should warn you, I do make a number of medium and sometimes large aggressions in this class. I'm way past microaggressions. So anyway, di over I equals to p dx. Integrate both sides. What do you got? We got natural log the absolute value of I equals the integral of p dx. And so I know it's end of class. So that says that I is equal to some constant times the exponential of the integral of p dx. But you should recognize that that's the integrating factor. So you can understand the integrating factor as being something I need to multiply the linear differential equation in order to make it into an exact equation. This is one way of understanding it. There's some other way of understanding it in terms of symmetries of differential equations, but well, we can talk about that every class if you want. Anyway, thanks guys.